Hi, welcome to this week's recitation. Today I will solve some recommended exercise in section 5.1. This problem is related to the theorem about subspaces. In previous recommended exercises, we introduced the subspace test. Back then, we didn't ask you to indicate that the set is non-empty, but from now on, remind you that if you want to use the subspace test and you want to show that a subset of a vector space is also a vector space, besides showing the closure properties, you also need to show that this set is a non-empty set. So for this exercise, you can just use theorem 5.1.1 in the lecture note. And remind you, you need to mention that it's non-empty in your proof. You need to make sure it's not an empty set in your proof. For exercises 3, 5, 6, 12, 18, 37, and 40. They are all related to the definition of subspaces. Because they are all very similar, so I will not do them here. You can use the same method in exercise 1 to solve these exercises. And here I'll give you a hint. They are all subspaces. For this exercise, the answer is no. You can prove it by the failure of the closure property of vector addition. First, we call this set S. Now we define V of alpha beta as 3 alpha minus 2 beta, alpha plus beta plus 2 minus 2 beta plus alpha, 5 alpha plus pi beta, and alpha plus beta. Now what you need to do is show that V of 0, 0 plus V of 1, 0 is not an element of S. Okay, first, we know that if two matrices are row equivalent to each other, then they have the same row space. So here, you just need to show that these two matrices are row equivalent to each other. So for this exercise, you need to show that these two matrices are row equivalent to each other, and use theorem 5.1.9 in the lecture note. Okay, first, from the definition of U, we have x1 is equal to minus x2 plus x3. With this, the description of the image of U by the mapping T can be written like this. T of U is equal to 3 times minus x2 plus 2x3 minus 2x2 plus 5 times x3 and 2 times minus x2 plus 2x3 plus x2 minus x3. And x2 and x3 are both real number. It's easy to show that it is R2, so I will not show that it is R2 here. Please check that it is R2 by yourself. For this exercise, the answer is no. The union of two subspaces is not necessarily as subspaces. Here we provide a counterexample. We let U be this kind of set, and W be this kind. Now, please check that the union of U and W fills the closure property of vector addition. By yourself. Before we find this exact condition, we need to prove a lemma first, and we call this lemma 1. That U be a subspace of a vector space V, and U prime are elements of V. If U is an element of the little u is an element of capital U, and little u prime is not an element of capital U, then little u plus little u prime is not an element of capital U. The proof of lemma 1 is not difficult, so I will leave that to you. Okay, now let's prove exercise 16. We let little u be an element of capital U and little w be an element of capital W. Then if the union of U and W is a vector space, then by the closure property of vector spaces, little u plus capital U is either in, little u plus little w is either in capital U or in capital W. Then here we can use the lemma 1 because little u plus little w is an element of capital U, so we have W is an element of capital U, or little u is an element of capital W. Then it gives us W is a subset of capital U, or capital U is a subset of capital W. For this direction, if the union of U and W is a vector space, then the one subspace is contained in the other subspaces. But how about the opposite directions? Trivially, the union of capital U and capital W, trivially, if U is an subset, if W is a subset of Q, or U is a subset of W, then the union of U and W is either W or U. So it is also a vector space. So the conclusion is the union of two subspaces is a subspace if and only if if only if one of the subspace is contained in the other one. So the union of U and W is a vector space if and only if W is a subset of U, or U is a subset of W. The hint of this problem in the back of the textbook has a typo. You should use theorem 9 instead of 7 to solve this exercise. Use theorem 5.1.9. And exercise 21 is an easy exercise, so I will not do it here. We leave it to you. For this exercise, I believe that some of you might get confused about the meaning of the smallest subspace containing a set. In linear algebra, we say a subspace W of a vector space V is called the smallest subspace containing a non-empty subset X of V if X is a subset of W, and for any subspace U of V such that X is a subset of U, we have W is a subset of U. With this definition, I believe you can work out the rest easily, so I will just leave the rest to you. The rest is left to you. This exercise contains two parts. For the first part, here we need to show that D of Pn is a subset of Pn minus 1, and Pn minus 1 is a subset of D of Pn. This direction is easier, so we leave it to you. for this direction. First, we let u be equal to an minus 1 t to the power of n minus 1 plus n minus 2 times t to the power of n minus 2 all the way to a0. And clearly u is an element of p n minus 1, and where ai is real. Now we want to find an element in Pn such that its derivative is u. So we let u be an minus 1 over n times t to the power of n plus an minus 2 over n minus 1 times t to the power of n minus 1, and all the way to a0 times t and plus a constant c, and is an element of Pn, where c is a real number. Here, since the derivative of v is u, we have u is an element of d of Pn. Therefore, Pn minus 1 is a subset of d of Pn. The second part of this exercise is very similar to the first part. So again, I will leave it to you. Similar to 1. For exercise 31, first we recall that for two matrices A and B, A is equal to B if and only if every element of A equals to every element of B. So here we will use this theorem to solve this exercise. First, we find the ijth entry of this matrix. And we can move the prereferences into the summation. So here we have UK, VK transpose, sub ij. And for this term, we can rewrite this term into the ith entries of UK times the jth entry of VK. And this is equal to A ik, and this is equal to B kj. So again, we can rewrite this into AIK times BKJ, and this is the ijth entry of the product of AB. So therefore, AB is equal to this matrix. This exercise contains 3 parts. In the first part, you are asked to show that the restriction of L to U is linear. This part is very easy, so I will not do it here. We leave it to you. For the second part, its domain is apparently just U by the definition. For the third part, the answer is no. L and the restriction of L to U does not necessarily have the same range. And here, I will give you a counterexample. We let L be a mapping which maps xy into x plus y, and we let U be the point on this straight line. Then it's easy to show that range of L contains all the real number, but the range of the restriction of L to U contains only 0. Okay, this problem is similar to exercise 1, as we mentioned in the beginning of today's recitation. Since the span of an empty set is defined differently in different textbooks, and an empty set is not a vector space, since a vector space must have the 0 vectors. So if you don't consider the case of empty sets, then you will miss the case of empty sets. So no, since an empty set is not a vector space. Okay, for exercise 34, first we let A be m times n, and B be n by k. Now we let AI be the ith column of A, and Bj be the jth column of B. First, we know that the column space of A is a subset of Rn. The column space of B is a subset of Rn. And the column space of AB is a subset of Rn. Then apparently the column space of AB is not a subset of column space of B if M is not equal to N. Even if M is equal to N, this is not necessarily happen. Now let's go to the second part. First, we know that AB can be written as A times B1, A multiplied by B2, and so on, A multiplied by BK. Now, with that, B BC1 times A B1 plus C2 times A B2 all the way to CK times A BK, where Ci is a real number. Then V can be written as summation from I equal 1 to K Ci times summation J equals 1 to N B BJK times AJ. And since this is a linear combination of the columns of A, so it's an element of the column space of A. Therefore, column space of AB is a subset of column space of A. Here I will give you some examples. If A and B are both identity matrices, then the column space of AB will equal to the column space of A and the column space of B. And if A is identity and B is not identity, and with that B be1 0 0 0, then the column space of AB is not equal to the column space of A. This problem is similar to exercise 36. If you take the transpose of AB, then you can just use exercise 34 to prove it. Similar to exercise 34. This exercise is just about the definition of column spaces, row spaces, and null spaces. So I will leave this problem to you. For the last three exercises, exercise 44, 48, and 49, these three exercises are out of the scope of section 5.1, so you can just ignore them. They will be covered in this Wednesday's lecture. They are out of the scope of section 5.1, and you can just ignore them. Okay, then we are kind of done here. Is there any question? Okay, then remind you that quiz 8 will cover recommended exercises 8 and 9. Then that's this week's recitation, and I'll see you next week.